Precision Launcher FEDD 2018 by Harper Williams, Brandon Sanchez, and Michael Salgado. How we implemented the engineering design cycle. We began the engineering design cycle by asking what exactly we needed to accomplish and what were our constraints. We were tasked with constructing a precision launcher capable of accurately launching a ball about 30 feet. We were limited in how big our launcher could be, the amount of energy except the potential energy of the 5-pound weight, and the amount of human intervention allowed. We were also allowed a $40 budget. Next, we had to begin brainstorming ways to solve this problem. Originally, we had looked at creating a sort of trebuchet or a modified oversized crossbow. After much debate, we decided on our current design. As part of the process, we drew some blueprints to aid us in construction. We estimated some measurements that we thought would be easy to work with, and we decided on our materials. Our materials included 2x4s, pulleys, springs, rope, screws, and door hinges. After constructing a prototype according to plan, we noticed that we had to change many parts, and we went back to the drawing board. The next model worked much better, although we decided to move away from bungee cord to springs. Improvements were made on almost every aspect of our design. We changed how big our barrel was, and we changed the elastic used to launch the projectile. We even changed the projectile itself multiple times. We continued the cycle many times until we had a working model. The main challenge we faced was figuring out how to use the weight to both load and release the projectile in the simplest, most effective way possible. By attaching the weight to the ball carrier, we were able to both pull back the weight and release it using a handmade mechanism. Another design challenge was creating the release mechanism itself. We went through several ideas before finally reaching a hook design that could be lifted when pulled over a wire. Since we had such an unconventional design, there was also a potential for risk because of our inexperience in designing and building launchers.
In our research, we had to take into account all of the forces that were acting upon our device before we began designing it. Our choice for a projectile reflects the findings of our research, which lets us know that the ideal projectile for our launcher would be one that had very low air resistance, like a ball. We also found that our ball would benefit from having a lower mass, as more force would be required to propel a more massive projectile. This led to us using a racquetball. Another critical component of our project that we learned through research was that our launcher had to be at an initial zero energy state, save for the potential energy of the weight. So, our launcher design featured a spring and pulley system only activated when the potential energy of the weight was converted into mechanical energy by dropping it, which was in turn stored in the springs through a pulley system as potential energy, which was then transferred into the ball as kinetic energy. This fulfilled the multiple energy transfers and zero initial energy state required by the rubric. Our project performed as well as we thought it would on FEDD Day, firing a very short distance. The reason for this seemingly failure in competition was because of a malfunction in our firing mechanism. The previous day, our launcher had worked, but when our firing mechanism broke from over-testing it, we were not able to achieve the same results which we had the day before FEDD. Because of this mishap, we ended up scoring 0 points, although we were ranked at the top of the list of the participants with no score. We believe this to be because we had a very interesting design.
The group believes that there were some definite flaws to the design and the final product. As stated, we had a large amount of difficulty in constructing a working model of the launcher as we had originally envisioned it. In fact, the piece which we had created in order to allow for the pulley to detach from the ball carrier was one of our largest problems. The wood from which we took the piece split more than once, which led to slowing down of the process. If we were to repeat the FEDD project, I do believe that 3D printing could be an alternative to creating such pieces as the aforementioned one. This could help because the plastic might be less likely to fracture and also could be more precise in the actual structure of the piece. Not only this, but there were some time management and pacing issues which caused for a time crunch towards the end of the project. If we were to offer advice to future freshmen who are tasked with projectile launcher in the FEDD project, we would strongly recommend having a working model well before the actual date of FEDD. This, of course, would allow for more time to fix design flaws as they arise. In addition to not procrastinating, one of the largest pieces we have to offer is to be as precise as possible in every move you take, regardless of the FEDD project you are tasked with completing. Slight mistakes in each part of the design can cause huge problems for the overall performance of the machine. The group suffered as a result of small errors littered throughout the project. Overall, FEDD was an invaluable experience in terms of our growth as students and future engineers. This is because we were able to get a better understanding of the engineering design process and some of the problems that engineers must routinely face. Thank you for watching.